個腦入邊。
跟那个厨哎，哦，很好呀，对哦。
你只唱兩個班，
我真係冇班，你真係掉班嚟嚇。我嘅班嚟，我真係冇，我真係冇掉班嚟定班。得到。
班你要咩？
得到。
我呢？
真係可以用，一定是對。
你現在呢？對我呢？對呢？我能現在，只能現在，不能現在，不能現在，快能現在，我能聊聊現在。
Because 能成 blog 成真正嘅我，能成 blog 成真正嘅我，高真正能成 blog 上。
爸爸。 Hurry up.
I was just looking to understand what the process of convection is, what the structures look like, how things behave and evolve. I didn't know what was going on, and so when I looked at the visualizations, it helped me understand what was going on. And then I would talk to people who actually observe the sun, and I'd find out what they were actually seeing. My name is Robert Stein, and I'm Professor Emeritus at Michigan State University in the Department of Physics and Astronomy. I guess from the very beginning, I was interested in fluid dynamics, which is how fluids behave. When we say fluids, we don't just mean water or things like that, we also mean gases. I was interested in the atmospheres of stars. I first started off doing some stuff in the evolution of stars, but again, that's sort of fluids because stars are gases, and you're interested in how they behave. Everything I've done in my research career has used computers. I think I have worked on almost every supercomputer that has existed. I started with an IBM that had vacuum tubes and a rotating drum memory with 2,000 words of storage, not bytes, words, but storage. You wrote the codes in and put it through some kind of pre-compiler, and it punched you out a new set of cards in symbolic assembly language, which you then put on the right place on the drum so that in the time it took to execute an instruction, the drum would have rotated around once to just reach the next instruction. As the power of computers increased, two things happened. We went to do more complex problems, including more physics, and we could do them on much larger scales. If you're studying something here on Earth, you can handle it and you can run experiments to see how it behaves. In astronomy, we can't take a chunk of the sun, and so we have to observe it from a distance. All of the information we get in astronomy comes from the light that we analyze. So astronomers have become experts on getting the last little bit of information out of light. Astronomers use telescopes mainly as a big light bucket. So our eyes, only a certain amount of light can go in them. You make something that's huge, and a lot of light goes in, and the bigger it is, the more light it can collect. We use as big telescopes as we can to get as much light as we can. When you have a lot of light, you can break the light down into very narrow color bands, and so you can get a lot more information out of it. There's a side effect also for the sun, which is what I'm interested in. Because the sun is close enough, we actually see its size. If you take a picture of it with a telescope and you can enlarge it, you can look at a little piece of sun, you can see fine structures on it. we can see things on the sun that are about 70 kilometers in size right now. And we're building a new telescope that should be able to see things that are about 30 kilometers in size. And for the sun, that's really very small scale. And of course, the more information we get means there's more stuff to model, because there's new things that we see that we never expected to see. So you've got to go back and want to model things on finer structures and shorter time scales, and so you need bigger computers that are faster, that can
first zoom test on sun. I don't have an actual solar filter, so I had to improvise. Don't mind the box, but yeah, that's it. I ordered it online. My girlfriend did, and I had no other way to put it on, so I had to use a box of condoms. But it's all good. Let's go fucking check this shit. Now, so you can see, boom, there's the fucking sun. Yep, it's pretty good.
The sun. Presented by Science at NASA. The sun. It inspires songs, warms us, and grows our food. Life on land and in the oceans, the daily weather, and long-term climate patterns happen primarily because of the energy we receive from our closest star. Even tiny variations in that energy can affect the workings of our planet's atmosphere. NASA uses instruments to follow the sun and monitor the amount of solar energy coming to us. The latest instrument to do so, the Total and Spectral Solar Irradiance Sensor, TSIS-1, makes those measurements with unprecedented accuracy. TSIS gathers information from its perch aboard the International Space Station, or the ISS. Flying on the platform that the orbiting laboratory provides has allowed TSIS to continue NASA's 40-year record of tracking the sun's radiant energy, one of the longest and most important climate data records gathered from space. Over the past several decades, Earth's ice mass has diminished, sea levels have risen, drought and precipitation patterns have changed, and growing seasons have shifted. To understand the causes, including human influences, of these changes, and to refine the models used to simulate Earth's climate, researchers must know the amount of incoming solar energy. Peter Paluski, TSIS lead mission scientist, explains, when there's a balance between incoming energy from the sun and the infrared radiation Earth emits, climate remains steady. An imbalance means energy is either being stored in the system, causing temperature increases, or lost, causing temperature decreases. Energy from the sun makes up half of the balance equation. Even though the measurement record shows that the sun's solar energy output has not had a major influence in recent climate change, that output needs to be monitored continuously. It is arguably the most important variable we need to know to understand climate, says Paluski. Trying to understand climate without measuring the sun's input is like trying to balance your checkbook without knowing your income. Climate is measured over long time spans, decades to centuries and longer, unlike weather that changes over small time scales. To be able to connect measurements over long time periods, continuity and accuracy are key. TESIS has two sensors. The Total Irradiance Monitor, as its name suggests, measures all of the radiant energy from the sun, and the Spectral Irradiance Monitor measures how that energy is distributed over ultraviolet, visible, and infrared wavelengths. The latter helps scientists understand where in the atmosphere solar energy is being absorbed. For example, TESIS spectral irradiance measurements of the sun's ultraviolet radiation are critical to understanding the ozone layer. Ozone in the stratosphere absorbs ultraviolet light. This heats the stratosphere and drives changes in atmospheric wind flow that can propagate down to the lower atmosphere and impact climate. So many factors influence Earth's climate, says Paluski. We need to continue learning how they all interact. TESIS is helping us characterize the sun's behavior and how Earth's atmosphere responds to the sun. For more science from the International Space Station, go to www.nasa.gov/ISS-science. To continue following our closest star, visit science.nasa.gov.
Something to do.
I'm so sorry. No need to avert your eyes from the sun on here. NASA has released new high-definition images taken by its space-based telescope. Naming the project Thermonuclear Art, the footage was captured by the American Space Agency's Solar Dynamic Observatory. It snaps a photo of the sun every 12 seconds in 10 wavelengths of invisible ultraviolet light. Each wavelength helps highlight a different temperature of solar material, and each is assigned a colour. At various times you can see solar flares, vast explosions of material bursting out of the sun's surface, and coronal loops of solar material streaming up and down the lines of the sun's magnetic field. It took a team of specialists about 10 hours to produce 1 minute of footage. NASA also recently released footage of Jupiter in 4K HD, showing changes in the planet's giant red spot.
Senyum sana. Meditasi itu. xíu để cứ giúp giúp. Cái đó là xanh. Cái chút hối. Chút là cả xanh hối. Tôi buồn quá.
I could get coin. I could get coin.
Anh nhìn gặp không?
Could coin. I could treasure. Treasure.
Xin chút rồi.
The treasure. The treasure. Treasure bị trôi lại.
Rất là tốt. ไม่